In this lecture, we're going to talk about the fundamental theorem of calculus. So finally, we'll be able to look at the relationship between the differentiation and integration. And this theorem turns out to be one of the most important theorems in calculus, the one that we're going to look at. Now, prior to this, if you remember, when we wanted to find the value of a definite integral, where we have limits of integrations going, say, from a to b, we had to do that through finding the limit of Riemann sums, right? And we know how tedious that was, a process that was reminiscent to finding the derivative using the limit of difference quotient. So it was very kind of painful, tedious process, even though we had some very basic functions. So you can imagine again the difficulty in doing that. So after this theorem, once we talk about this theorem, then our life's going to be a heck of a lot easier, much easier in order to find these definite integrals. We'll be able to find them with little effort. Okay. So before we actually look at the fundamental theorem of calculus, let's go through this first theorem, which will be used in proof of the fundamental theorem of calculus, a theorem that was developed by Newton and Leibniz around the same time. And there is some documentation that the fundamental theorem was known even prior to Newton by other people. Okay, so let's begin by defining what we mean by the average value of a function. Notice if you look at theorem 1, the mean value theorem, these two kind of look the same, right? The two expressions look the same. In the first instance, where we have the AV means average, and the average turns out to be a function at C. Okay, so first of all, the average value of function. If a function is integrable, remember what integrable meant. Integrable means the limit of the Riemann sum exists. So if a function is integrable on the closed interval from a to b, then the average value of the function over an interval is given by the definite integral from a to b of f of x dx divided by b minus a, the length of the interval. Okay, now we have a figure here. So we got figure 1, figure 2. Figure 1 is the one on the left. This is figure 1. Okay, so the geometrical interpretation of that definition, if the function is positive, notice that in the definition there's no hint to that. So if we assume the function is positive, then we can relate it to an area under the curve. So what we're saying is that this area under the curve, essentially, which we called it by definite integral from a to b of f of x dx, that area could be written as the area of some rectangle whose length is the distance from a to b and whose height is the value of the function, which is called the average value, f average. And there you go. So this area is going to equal to the area that I shaded earlier. Okay, so that would be the interpretation of this expression, of this definition. Now, we know that we can actually, and this is by intermediate value theorem actually, which we'll show you in a moment. So because the function is continuous, then that f average right here is going to be the same as the value of the function at some point c. We will be able to attain that, and that's because the function is continuous on a closed interval. Okay, so if I rewrite this average value of a function to kind of reinforce what I mentioned as far as the area under the curve from a to b, which includes this part also, the upper part, that area would be equivalent to the area of a rectangle from A to B. Now from this, if we cross multiply or multiply both sides by b minus a, then f average times b minus a is equal to the definite integral from a to b of f of x dx. And again, that's what this says. Remember, integral from a to b is going to be the area under the graph of f, right? And f average times b minus a, that's going to be the area of some rectangle, right? And that's what that means. Okay, so let's take a look at our mean value theorem here. The mean value theorem says that if the function is continuous on a closed interval from a to b, then there exists a number c so that we can attain the average value of the function, right? F at c would equal to 1 over b minus a times the definite integral from a to b of f of x dx. Okay, so if we take a look at the proof of this one, right? It's not difficult to prove this one. So the proof goes something like this. Well, because the function is continuous on a closed interval, right? So we can say that we had the theorem earlier, by extreme value theorem, right? Extreme value theorem. We can say that there is a minimum and there is a maximum value of a function which function lies in. Okay, that's extreme value theorem, that f of x lies between a minimum and maximum. Okay, and extreme value theorem guarantee the existence of the absolute max and minimum on a closed interval. So this is from extreme value theorem. Now, using properties of definite integrals, I believe this was in section 4, the previous section just to this one. Okay, using properties of definite integrals, we also know as the following. This just follows from the property of definite integrals. Okay, and we're going to have m times b minus a less than or equal to the integral from a to b of f of x dx less than or equal to capital M times b minus a. Okay, now in here, remember when we write the definite integral from a to b, so that would imply a is less than b, right? So if a is less than b, then that would mean b minus a is positive, right? The difference between them will be positive. And in this inequality, this one, if I divide everything by b minus a, I don't need to change the sense or direction of inequality. So I'm going to get 1 over b minus a without changing the direction of inequality. A to b of f of x dx and less than or equal to m. And remember again, here is the minimum and capital M is the maximum. Right? Okay. Now this value that's inside, this is going to be some y value, right? This is going to be a value for y, call it. Now at this point, we're going to cite another theorem. So I can say at this point that by intermediate value theorem, right, by that theorem, then we know that there's at least one c, right? There's at least one c such that let me call it the y value is equal to f at c, right? Okay, well the y value, we're gonna let it be what's inside right in here. Okay, Therefore, we can say that f at c is equal to 1 over b minus a, the integral from a to b f of x dx. Okay, and there you have it. Okay, and that proves, again, the mean value theorem. So we now can move on to actually stating the fundamental theorem of calculus. Okay, so let me put up that theorem here, and then we'll talk about it. Okay, so we are now in a position to discuss the fundamental theorem of calculus. It comes in two parts. Now, part one, remember I mentioned in the beginning, the fundamental theorem actually establishes the relationship or the connection between differentiation and integration, right? So that's what part one does. It relates the definite integral to the derivative of the function. Okay, so the theorem goes, if the function f is continuous on a closed interval, then the function f if it's continuous on a closed interval, then the function is defined by this. This is how the function f, capital F, is defined on that closed interval. This function is differentiable, and its derivative, which is the general derivative notation, the derivative of the function, ends up being just f of x. Remember, f of x is actually the integrand here in our definite integral. Okay, so that's the connection between the integral and the derivative of the function. So if we take a look at the proof of the fundamental theorem part one, we can let's do the following. First of all, I'm gonna graph. This is some function, let's say starting at a, and here this would be x, and then we're gonna go some units later, x plus h. Remember, h here is a tiny distance away from x, but I'm actually exaggerating. In fact, let me extend h to be all the way here. Okay, so this point is therefore going to be x plus h. Okay, x plus h. And if I look at let's say f prime of x, okay, here f prime of x, using the definition of the difference quotient, limit of difference quotient definition of derivative. So we want to find the derivative of this function. Okay, so its derivative is going to be f at x plus h, remember the difference quotient, minus f of x, and then we're going to divide that by h, right? And we assume, of course, h is not 0 here. We approach in h, but h isn't 0. Okay, now of course, and you can see here x and x plus h, both of those must be inside this closed interval from a to b. And the interval b here, there you go, and this would be, let's say, b here. Okay, now I can actually write f at x plus h here, right? I'm going to write f at x plus h in terms of the, like, again, assuming the function is positive, but it doesn't have to be, but for the geometry of this to be a little easier, if I take a look at f at x plus h, so we're looking at the integral from a to x plus h, so that would be this shaded region right there. That's what capital F at x plus h is. So I can write this as the limit h approaching 0 of the integral, definite integral from a to the x plus h of f of t dt. Usually when the limits of integration involve a variable such as x, we make the argument of the integrand of the function different from that variable. That's why it's t now. Okay, so that's f at x plus h minus f of x is the function that was defined in the fundamental theorem, the integral, definite integral from a to x of ft dt. Now the integral from a to the x ft dt, that's just going to be this portion, right? The highlighted region, that's what that is, right? From a to x plus h is the shaded region, the hatch, the one I have hatch, and the other one that's being subtracted is actually this part. So what we're looking at in the numerator, therefore, all of this equals to the area under the curve from x to x plus h, right? That's all that is. Now, let's divide this by h. Okay, and the next step, I'm going to actually now write this as the limit as h goes to 0, looking at that shaded region again. First I hatch this region from a to x plus h, then we take out the highlighted region, so what we have left is the integral from x to x plus h, right? So we can actually derive that here this way also. This integral, I can change the limits of integration from a to x, go to x to a, and the effect of that, remember the property of definite integrals, that changes the negative to a positive. That's going to be ft dt, and then plus the integral from a to the x plus h ft ft dt. Okay, now we can actually join these two definite integrals. Remember, one of the properties was an integral from like x to c, and then we have c, or actually when we talked about properties of definite integrals, it was a to c, c to b. Combine it, you get the integral from a to b, right? That one. So that's what I'm using here. Okay, so we're going to join the numerator as 1. That's what it amounts to. So this is going to be equal to the limit as h goes to 0 of the integral, therefore, from x lower limit to the upper limit of the second one, ft dt divided by h, right? Now, remember the mean value theorem. The mean value theorem told us that we can write the definite integral right up here. We had it. So we can write the definite integrals, right? The definite integral as the area of some rectangle, right? That's what this is. So using this notation by mean value theorem, we can actually write the numerator of this expression as, this would be the limit h approaching 0 of f at c times h. H is the length of that rectangle, the distance from x to x plus h. And that's going to equal to f of x. Okay, now this follows for the following reason. Remember, for the mean value theorem, c lies between x and x plus h, right? So we know that as h goes to 0, c approaches x. So when we take it in a limiting sense, the h is here cross, and there you go. So f at c approaches f at x as h approaches 0. So if you want, we can actually change the lower limit if that would be equivalent to c approaching x, like from the right side. True? And that's the justification for it, and that proved what we wanted to prove. We just found f prime x. So that's actually pretty easy, right? All that means is that if we have the function in the form of a definite integral, then the derivative of it is just going to be the integrand. That's all you got to do. So this makes differentiation very easy for those definite integrals. Now this is important because here is a variation of the fundamental theorem calculus part 1 for when the upper limit of integration, remember it goes from a to x, right? When the upper limit is actually a function of x here. So this is part 1 for where u is a function of x. Okay, and in this case, ddx, the derivative of the definite integral from a to, let's say, g of x, a function of x now, not just x, it's going to be ft dt. Okay, for the fundamental theorem, for the way it is, to work the way it does, the upper limit has to be x. Okay, so if it's something other than x, like x cubed, square root of x plus 5, sine x, whatever, that's what we mean by function of x, then it's done differently. So this one, the derivative is actually going to be f of g of x. It's going to be the composition and then times g prime x. So that's what the derivative is going to be. Okay, and we can actually prove this one too. To prove it, and here's the proof. So remember, u is g of x in this case, which by that we get g prime of x is the derivative, right, of u. Therefore, if I want to find the definite integral as a function of u this time, by fundamental theorem part 1, that's the integral from a to u of ft dt, right? That's part 1 of the fundamental theorem. Okay, this one, if I take the derivative of both sides, then dx of f of u is going to equal to the u and then fu, that means the derivative, right, of a capital function f of u times chain rule, right? That's the x of u. That's because of consequence of chain rule. Okay, and by fundamental theorem part 1, this derivative, right, that's just going to be the integrand, which is f u, and of course this would be chain rule dxu, and f of u, but u was a function of x, so that's going to be f of g of x times g prime x, right? That was our dxu. That was up here. So there you have it. Okay, now how is this going to help us? Let's say do a couple of examples here. Alright, so I have copied some exercises here. Let's take a look at the ones I have circled. So we're going to begin with exercise number 4. These are going to be fairly quick. In exercise number 4 question, find derivative of the function. So notice here this time the function is actually the definite integral, right? That's the function. So according to the fundamental theorem, in number 4, g prime of x, check this out, it's going to be just x square root of x squared plus 1. That's it. So you just take these t's, replace them by x's. And notice, by the way, it doesn't matter this number -1 over the interval from a to b, right? It doesn't matter. The answer is just going to be what we have here. Okay, but the upper limit has to be x for this to work. Now in number 6, what's different in number 6 is that if you look at the limits of integration, they go from x to 3, right, of t over square root of t plus 1 dt. So the limits are in improper form, so I need to actually switch the limits of integration. It has to go from a, means a number, to x. So anytime we change the limits of integration, remember there's going to be a negative in front of the integral. Okay, so that's the offset. Changing the limits of integration changes the integral to a negative. And then of course, whatever the integrand, unaffected by that. So this answer is going to be what? It's going to be just negative. You replace t with x's. And there you go. X over x plus 1. So that's again the connection between, would be like the area of under the curve, and the derivative, of course, is, here, let me, I did something incorrect, hold on. I just wrote the answer for you. So that's just the integral, and then h prime x, there you go. H prime of x is going to be negative x over square root of x plus 1, there in number 6. And again, that's the connection between the area under the curve and the slope of a tangent line. Okay, that's what part 1 does. Now, in number 12, here we have g of x is equal to the integral from root x to 5 of sine t squared over t dt. Now for this one, again, we need to change the limits of integration from a number. It has to start from a number, okay, and then go up to whatever the upper limit ends up being. And the integrand, we don't do anything to the integrand. dt means that's the variable of integration. Okay, now notice here we have square root, right? So square root of x is actually, this time u is square root of x, right? Therefore du dx is going to be 1 over 2 root x, right? Or simply du is 1 over 2 root x dx. True? Now we can work this one. So the answer to the derivative, this is still the integral, right? At this point, that's just gx. So g prime x is going to be negative sine of x squared, right? Sine of x squared over x, true, and times the derivative du dx, which is 1 over 2 root x, true. And at this point we can actually oh, I see. See, we're gonna plug in square root of x, and here's when we plug in for t squared, that's gonna be root x squared. Okay, we plug in the upper limit in here. All right, and then 1 over 2 root x. And now we can simplify this one as negative. The numerator is just sine x, true. Denominator is going to be, and that means down here too I have root x, right? Because we plug in root x for t. That's why I didn't do that. I just put x. Okay, that looks right now. So it's going to be sine x over root x, and then of course we have the 1 over 2 root x, and the final answer is negative sine x divided by 2x, and that's going to be the derivative. So that's how you work these exercises in this segment. Now let's take a look at the fundamental theorem part 2. Part 2 is kind of more exciting than part 1. So let me bring part 2 in here in my note now. Okay, so here is now part 2 of the fundamental theorem. So for part 2, which is a consequence of part 1, but this, to me, this is very useful because we're going to be actually doing more of this than part 1 going forward. Now, in part 2, the theorem reads, if the function f is continuous on a closed interval, then the definite integral is simply f at b minus f at a, where capital F is any antiderivative of f. That is f prime equal little f. Okay, so that's really great, because from here on out we can just find any antiderivative of the function, right? And we're going to look at the proof of this in a moment, but any antiderivative of the function would work. Remember, antiderivatives, there's a whole family of them, right? That's separated by a constant. So we can choose any of them, it doesn't matter, and we'll be able to evaluate the antiderivative at the upper limit and the antiderivative at the lower limit of the integral, and this now prevents us, or not preventing us, but it actually helps us do away from finding the limit of Riemann sums. Okay, so let's take a look at the proof of this one, which isn't really actually difficult. You would think it may be more complicated, but it's not. So if you look at the most general form of antiderivative, right, g of x here, and this is by Fundamental Theorem part 1, right? We can write it g of x as a to the x f of t dt. Okay, now if I let capital F of x to be even more general form of g of x plus c, this is where the whole family of antiderivatives are. Okay, so if I let it be that, now in here, by letting x be a, okay, so the lower limit. Okay, so we're going to put a in here, and we're going to put a in here. Okay, so what that would mean is this: f at a is equal to g at a plus a constant, right? Now g at a, that's when we can write it as the integral from a to a now, because right, a is x, from a to a of ft dt, and plus a constant. But then remember, if the limits of integral, lower upper limit, are the same, then the whole definite integral will be 0. So f at a is constant. Okay, so the constant, we established the constant is f at a. Now, for the upper limit of the same integral, okay, the upper limit of that integral, let x be b. And if I go to, again, the antiderivative, f at b is going to be g at b plus a constant, right? But then the constant, we found it to be f at a, true? So my next step, I can write g at b, right? G at b is equal to f at b minus c, which would be f at b minus f at a, true? Now g at b, from part 1 of Fundamental Theorem, g at b, that's going to be the integral from a to x, but x is b now, a to b of f of t dt, and that's equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. And notice there is no constant in this. There is no constant of integration, that is. Okay, and there we have it. That would be the proof of part 2 of the Fundamental Theorem. Okay, and of course we're going to look at some exercises here in a moment, but from this moment on we'll be able to find the definite integrals using Fundamental Theorem part 2 rather than using the limit of Riemann sums. Okay, so that's what this theorem 3 was. And then we have these other theorems. Let me just maybe write it, theorem 4. Okay, and this has to do with integral of odd even functions. So let f be continuous on a closed interval from a to b. But then in part A, if the function f is even, then the integral from negative a to a of f of x dx would equal to twice the integral from 0 to a of f of x dx. Okay, that's what that is. And in part B, if the function is odd, then the same integral from negative a to a of the odd function now is going to be simply 0. Okay, and there we have those. I believe the proof of these are in the book if you're interested in seeing the proof. Okay. So remember, for even function, we can go 0 to a and double up on that area. For odd function, is simply 0. Now this actually helps us quite a bit here, because you will see later on, fundamental theorem, we have to plug in the upper lower limit into the antiderivative, right? Well, the lower limit 0 a lot of times results in just 0 for that portion of the integration process. All right, and I believe that is all. So let's actually take a look at more exercises. Let's take a look at these exercises. I've circled the ones that I'm going to work them in this video. Let's begin with exercise number 16. Okay, in all of these, we want to evaluate the integral. That's what we want to do. Okay, so let's take a look how this is done. Number 16. Let's start with that one. Exercise 16, we have the integral from 0 to 2 of 2 negative 4u plus u squared, and then du. Okay, so the way we do this is just like the indefinite form. Remember, with indefinite form we have a constant of integration. With definite, now definite means we have limits of integration on every one of these. With those, we no longer have constant of integration. So that's why they're definite. We get a definite antiderivative, one that works. Okay, so the integrating every term of this polynomial, term-wise integration, makes this 2u negative 4u squared over 2, that's 2u squared plus 1/3 u cubed. Okay, now here's how we're going to do. When we write this, evaluated, this vertical lines means evaluated from 0 to 2. Okay, and at this point, we're going to use the fundamental theorem. So we're going to plug in the upper limit in for u, and then subtract the lower limit. Well, the upper limit is going to be 2 times 2, negative 2 times 2 squared, plus 1/3 times 2 cubed. That's the upper limit. The lower limit, on the other hand, the lower limit is going to be, when you plug in 0 in for u's, well, all of those become zeros, right? So I'm just going to go minus 0. And the step that we just did, that was the fundamental theorem of calculus part 2. Okay, then we can finish this off. That's going to be 4 minus 8 plus 2 cubed 8 divided by 3 is 8/3, right, which is what, 2 2/3. So the whole thing, to give it a denominator of 3, like, so that's going to be 12 minus 24 plus 8, and the whole thing is going to be negative 4/3 there. And don't worry about the area under the curve at this point. Okay, we just want to find the value of definite integrals If the function is positive over the interval from a to b, then of course we can always relate it to the area under the curve. Now I have the integral from 1 to 0 of t to 1/2 negative t to 5/2 and then dt. Okay, so for this one, this is number 22 now. The integral of t to a half plus 1 would be 3/2, so it's 2/3 t to 3/2 negative. 5/2 plus 1 is 7/2, so it would be 2/7 t to 7/2 from 1 to 0. Okay, now if you wanted to notice the limits of integration or in improper form, we can actually change them or keep them the same. Now you plug in the upper limit, you get 0 of course, minus the lower limit. We plug in 1 for t. 1 to any power is 1, right? So that's just going to be negative 2/3 negative 2/7. Okay, and the whole thing is going to be 21 is the LCD, 21 by 2, 42, and I'm sorry, LCD is 21, so 7 times 2, 14 minus 4, so that's going to be right, 21 is the LCD, 7 times 2, 14, 3 times 2 is 6. If I build each fraction, second fraction, multiply top bottom by 3, that's how I got 6. So that's going to be 8/21, negative in front makes it negative 8/21. Okay, now had I swapped the order of integration, we're done with this, but just to show you, you put negative here, right? Of t to a half minus t to 5/2. And of course, now move the negative throughout. That's going to be the integral from 0 to 1 of t to 5/2 minus t to a half dt. I'm just showing you how you get the same numbers by switching the order of integration, but you got to remember, put negative in front. So that integral will be the same, right? 2/3 t to, oh, actually, I swapped them out. So 5/2 plus 1 is 7/2, so it's going to be 2/7 t to 7/2 minus 2/3 t to 3/2. Evaluate it from 0 to 1 now. Upper limit gives you 2/7 minus 2/3. Lower limit gives you 0 when you plug in 0 for t. And 2/7 minus 2/3, the LCD is 21. That's 6 by 2, 3 by 2, 6 minus 7 minus 2, 14. The answer is negative 8/21. So you see, changing limits of integration is also an option here. In number 22, let's look at number 26, this one. Number 26, the integral from pi over 6 to pi over 4 of cosecant cotan. Okay, in number 26. So that's going to be pi over 6 to pi over 4 of cosecant cotan. Okay, and the whole thing is going to be, remember, the antiderivative of that's going to be negative cosecant theta. We don't have constant of integration, no more plus c. But with indefinites, we always need c. Keep that in mind, please. That will come up later on, where we have indefinites and we got to work them. Okay, so upper limit, that's going to be negative of, so I'm looking at cosecant of pi over 4 minus cosecant of pi over 6. And you can move the negative throughout if you like. Now cosecant of pi over 4, that's cosecant is 1 over sine, so it's going to be root 2, right? Because it's reciprocal of 1 over root 2. Sine of pi over 6 is 1/2, so cosecant of pi over 6, 1 over sine would be 2. So the answer is going to be 2 minus root 2. There you have number 26. Okay. Let's take a look at another one. We're going to look at number 30. In number 30, the integral from 0 to pi of square root of sine x minus sine cube. Okay, this is going to be interesting. Number 30. So it was 0 to pi of square root of sine x negative sine cubed x dx. Now I got to work this a little bit, first of all. So that sine x I can factor, I get 1 minus sine squared x, right? In the radicand, inside the radicand. Now 1 minus sine squared, that's cosine, right? Cosine squared x. True? Now, when we take the square root, let's work out the square root. When we take the square root, because we have product in the radicand is product, so that would be root sine x, and then square root of cosine squared. Remember, when you take square root of x squared, the answer is absolute value of x. So I get absolute value of cosine x. Okay, let's go to integral and do that. So our integrand, in other words, is going to reduce to square root of sine x times absolute value of cos x dx. Now, because in the 0 to pi, the interval from 0 to pi, cosine could be negative, right? So you gotta be careful how we're gonna write this thing in. Okay, absolute value of cosine x. In other words, there you go. The function, let's say if I'm looking at cosine x, remember the cosine x looks like this, right? Between 0 to pi, and this is pi. So I don't need this portion of the graph, right? We're looking at this portion. And absolute value of it, what even this part of it, let me go there. This is pi. So absolute value cosine x is actually going to be like that. This portion reflects up here. Now, but in 0 to pi again, remember from in the second quadrant cosine is negative. So here's how we're going to have to rewrite, all said and done. The integral, I'm going to have to break it into 0 to pi over 2 of the square root of sine x. Now I can write it as just cosine x, because in the first quadrant cosine is positive, right? So absolute value of x equals, remember x is if x is positive, and be negative of x if x is negative. And cosine will be negative in the second quadrant. So first part is going to be positive minus pi over 2 to pi of square root of sine x times cos x dx, right? Okay, so this is how we can get the integrand without the absolute value. That's the only way to get rid of the absolute value here. Okay, now we can actually proceed with our integration. Now, we can actually go through a, let's see, we can go through substitution method, right? If I let u be sine x, then du, derivative of sine, is cosine x dx, right? And the fact that I have it here, cos x dx, we're going to see this as the square root of u times du. Okay, and I'm going to work this as indefinite integral. So indefinite integral of a square root sine x cosine x dx. That's just going to be square root of u and then du. That's going to be u to a half du. A half plus 1 is 3/2, so that's going to be 2/3 u to 3/2, right? Now as indefinite, we have a constant of integration, right? So what I can do now is I can do the following. I can write this as the integral of 2/3 sine x raised to 3/2. Right? That's the first integral, and then evaluate it from 0 to pi over 2. Now, for the second part, it's the same integrand, right? Both of them are the same. It's going to be another 2/3 sine x to 3/2 with the limits of integration from pi over 2 now to pi. Okay, and I can directly substitute 2/3. The upper limit, sine of pi over 2, sine of 90 degrees is 1, so that's 1 to 3/2 minus sine of 0 is 0. I just did the fundamental theorem part 2, minus 2/3. Upper limit, sine of pi is 0, 0 to 3/2 is 0, minus lower limit gives you sine of pi over 2, which is 1, 1 to 3/2, which is going to stay as 1. Right? Now, within parentheses, I have 1, both of them here, right? So that's going to be just 2/3 minus negative 1 to 3/2 is -1, and negative in front makes positive 2/3. There you go. So the answer is going to be 4/3. Okay, and there you have it. Now, this is what we finished. Again, we finished this one using the original variable sine x, and right in here, it helped that I worked it as an indefinite integral. Now, let me just make a point here, folks. Okay. So we're done with this exercise, but let me make a note. This is important, and it will follow you for many courses beyond what we're doing here, what I'm about to show you here. Let's look at the integral, the one that we just did, the simple one, 0 to pi over 2. It was of the square root of sine x cos x, right? Cosine x dx. Now I worked it as indefinite integral, right in here. That means I didn't put limits of integration. So if we were to do this using definite integral, I let u be sine x, true? Du turned out to be cos x dx. No worries there. So we just did that. Now here's what's very important. If I rewrite this integral now in terms of u, it's going to be root u du, right? Again, that we just saw up here. So nothing's changed yet, right? Now here's where you'll see a change. If I attach the limits of integration and I go 0 to pi over 2, isn't that what those were? Right? 0 to pi over 2. That would be incorrect. Okay? So when you change your variables from one to another, you have to change the limits of integration. Let me write that, and please make a mental note of this for many years to come. Okay? Changing variable of integration changes limits of integration. Now, you can find the special cases where that's not going to happen, but I'm talking in general. So let's take a look at this one, see if it works with this one, what I just said. So, when x is 0, let's look at that. When x is 0, at x equals 0, u would be sine of 0, and sine of 0 is 0, right? So here's a case where lower limit didn't change at all, right? Now, let's take a look at pi over 2. At x equals pi over 2. U is going to be sine of pi over 2. And sine of pi over 2 is sine of 90-degree angle is 1. And check this out. You see? The limits of integration changed, didn't they? So that's very important. This is the most common mistake students make in, especially in Calc 2 and even Calc 3. They forget this and they just attach the original limits of integration with the new variable. Now let's proceed and see what happens. The integral of squares of u du, we just did that one up here, in fact, right? That's the integral. Except I don't need the constant of integration. So that's going to be 2/3 u to 3/2 evaluated from 0 to 1. Okay. And now I can write that as 2/3, 1 to 3/2 minus 0 to 3/2 is 0. 1 to any power is 1. So the answer is going to be, let's see. 2/3. That's fine. Don't look at this answer, right? Because I only looked at half of it. I only looked at 1/2 of this problem. Okay. So, and what's important is that we got 2/3, right? This was 2/3, and we got the exact same. Excuse me. We got the exact same answer here. So both of those are 2/3. You see that? Alrighty, and throughout the course I'll try to do that. I try to change the limits of integration and then work it with new limits. Okay, we're done with that exercise. Sorry, I keep scrolling up and down here, back and forth. Try not to let it bother you, okay? So we did number 30. Let's take a look at exercise number 32 now. In number 32, we have the integral from negative pi to pi over 2 of f of x dx, where f of x is given by this piecewise function. Now, if the function is negative, it's going to be a quadratic function. If it's positive, it's going to be cosine from negative pi to pi over 2. Okay. So this will be in number 32. From negative pi to pi over 2 of f of x dx. And this will be integral from negative pi. So we're going to go negative pi to 0 because our piecewise function went two different pieces, right? The cutoff was at 0. So for negative x's, it follows that piece. For positive, which is 0 to pi over 2, for positive x values, it's going to follow cosine function. That's it. You can graph these and you don't have to, but you could and see what's going on. This isn't complicated to do, right? X squared plus 1 looks like that, but this is only good this portion of the parabola. That's for x less than 0, right? And for positive piece follows cosine at x is 0. There you go. From 0 to pi over 2, so that means right in here. I only need this portion of it. There, that's the graph of this function. But again, it doesn't matter for what we're doing. The graph doesn't matter here. That part is cosine, and this piece is the parabola x squared plus 1, and here's where 1 is. Alrighty. So the integral, first of all, of x squared plus 1, that integral, call it I, is going to be 1/3 x cubed plus x evaluated from negative pi to 0. It has to go from low to high, and it does the limits of integration. Lower number on the bottom, higher number on top. The integral of cosine is going to be sine because the derivative of sine is cosine. That goes from 0 to pi over 2, and that's it. Now the upper limit inside the interval, you plug in the upper limit by fundamental theorem, you get 0, right? Minus the lower limit is when you plug in a negative pi in here, right? For the lower limit, I'm going to get negative pi cubed, that's x cubed, over 3 plus negative pi, which makes it negative pi, right? And then plus upper limit of sine of pi over 2 is 1, sine of 0 is 0. And tidy up this work, so we get pi cubed over 3, double negative, distribute, plus pi plus 1. And there you have the answer to this one. Notice how fast, how easy we can do this thanks to Fundamental Theorem Part 2. And we'll see in part of the exercise where now we can actually write the limit of Riemann sum for these complicated integrands. Alright, we did number 32. Let's take a look at the next three. 36, 42, and 46. 36, 42, 46. In exercise number 36. So the question reads, evaluate the integral of from 1 to 5 of the square root of 2x minus 1 dx. Okay. Now, to do this one again, if you want, we can, because this is function composition, right? For function compositions, we have to introduce a variable. So we're going to let u, for instance, be 2x minus 1, the inside function. 2x minus 1. That means du is 2 and then dx. Now, let me change limits of integration. Remember, anytime we use a u substitution, we have to change the limit of integration. So, here is when x is 1, u would be 2 times 1 minus 1 or 1. Doesn't change. Coincidental, pure coincidental. When x is 5, u would be 2 times 5 minus 1 or 9. That changed. So call this I. The integral is going to be that of 1 mapped onto a 1. Let me use different color, by the way, just so you're aware that the limits have changed. So it's going to be 1 to 9 now, right? The limit of integration changed. Of the square root of u, and 1/2 du is dx, right? Du doesn't equal dx. This is 1/2 du times 1/2 du. All right. Now I can actually integrate this, so it's going to be 1/2. The integral of square root of u, that's u to a half, would be 2/3 u to 3/2, evaluated from 1 to 9. Okay. And now I can actually work this one. The 2's cross out, so this is going to be 1/3. 9 to 3/2 minus 1 to 3/2. Now 9 to 3/2, that's square root of 9 cubed. That's 3 cubed minus 1. 26 thirds. That's going to be the answer. Okay. The alternative, some people like doing it this way. They don't like the fact that you have to change the limits of integration. So the alternative is to work this integral as an indefinite, means don't put the limits on it. And in the end, once you have your answer, which is going to be like 1/2 and then 2/3 u to 3/2 plus a constant, you replace u with x, the original, whatever you let it be, 2x minus 1 in this case, and then attach the old limits. So let me show you that. I'm just going to do this one time so we're not double doing it every problem twice. So the integral, in other words, would be, I'm looking at this portion. So the answer to that was 1/3, right? 1/3 u to 3/2, right? Plus a constant, the one that I just did. So that means the answer to the original exercise is going to be See, there you go, 2x minus 1 raised to 3/2 evaluated from 1 to 5. There, you can do that. So work it as indefinite with a constant, and then replace it with the original substitution, what you let u be, and the original limits of integration. All right, so that's going to be 1/3. 2x, that's 2 times 5. I'm doing fundamental theorem. Upper minus lower limit. 2 times 5, 10 plus 1. That's going to be, let's see. Yeah, that's going to be 11 to 3/2, and then minus 2 times 1 is 2, is 2x minus 1. Sorry, I knew something wasn't right because of the 11. Didn't like that. Yeah, it's 2x minus 1. So 10 minus 1, that's going to be 9. Better. 3/2 minus 1 to 3/2. Again, 9 to 3/2, that's square root of 9 cubed. That's 27. 1 to any power 1. 1/3 times 26. So we get exactly the same thing here. Okay. And let's see. Next, what are we going to have here? Number 36. We're done with 36. The next one was number 42. In number 42, the integral is from 0 to pi over 2 of square root of cosine theta, and then sine theta d theta. Okay, so for number 42 now, we're going to make a u substitution in this one. Okay, so we're going to let u be cosine theta. That means when theta is 0, u would be cosine of 0, which is 1. And when theta is pi over 2, u is going to be cosine of pi over 2. Cosine of 90 degrees is 0. Okay, let me move this away. We'll do those later. So this is going to equal the integral from when it's 0, you get 1. Let me move below. So I is equal to the limits of integration now go from 1 to 0 of u to a half. Now du, derivative of cosine, is negative sine, right? Negative sine theta d theta, and I have only sine theta d theta, so that means I'm going to make this negative of du. That's negative of du, right? Negative of du will make that positive. And now, because the limits of integration are not in a proper form, right? We always go lower first, higher second, on top. So I'm going to change the limits of integration. That makes this negative, turn it into positive. 0 to 1, u to a half du. Now the integral of u to a half, again, u to 3/2, so that's going to be 2/3 u to 3/2. From 0 to 1, upper limit makes it 2/3 times 1 to 3/2 minus 0, the lower limit. The answer is just 2/3. Okay, so for number 42, that wasn't bad. And then we said we'll do number 46. In exercise number 46, this time we want to find the integral from negative pi to pi of x squared sine x divided by square root of 1 plus x squared. Now for something that is this complicated, even with a u substitution, this isn't going to be easy because we have a mixture of transcendental function, sine x, and of course we have algebraic expressions. So then that means there is a catch to this one. Okay, at this point. Now, we can note that this integrand, the function that's inside the integral, the integrand is going to be, let's see if it's an odd or even function. Okay, so what I want to do, I want to do f at negative x. So that's going to be negative x squared sine of negative x divided by square root of 1 plus negative x squared. That makes it x squared. Sine is an odd function, right? So sine of negative x is going to be negative sine of x. And the denominator, of course, the same, unchanged. 1 plus negative x squared is just 1 plus x squared. Right? Now I can bring the negative in the numerator to the front, so this becomes x sine x divided by 1 plus x squared square root of. And this is negative f of x, right? So we just showed f of negative x equal negative f of x. That would mean it implies that f is odd. And remember, for an odd function, we had that part of that theorem, integral from negative a to a fx dx is 0 if f is odd. So there you go, all of that is just 0 without going through any trouble at all. Now for this to happen, you have to have a symmetric interval, right? It's got to be the same number. So if this question was integral from 2 to pi, 0 to 3, whatever else, then we'll be in trouble. Wouldn't be this easy. All right. So there you go. That's number 46. Now I think let me see. That's pretty good. Let me go back up, and I think that's as far as I had my exercises. 48. Okay, let's do 48 is the same thing, right? So notice in 48 we have negative pi over 4 to pi over 4. I have a mixture of trig and algebraic, so that just tells me I have to check for even or oddness of this one, right? And again, because tangent is odd, so the numerator, when you go change x to negative x, that becomes negative tan x cubed. The denominator stays 1 plus x squared, so that's negative f of x. Yep. So the integrand is odd, right? The integrand is odd, so that means the integral will be 0. There, we just did that one. And what I meant by the integrand means actually this whole thing, okay, not just the denominator. And that's the answer to that one. Now actually we can do one of these. So for this one now, let's take a look. In exercise number, these won't take long at all. These are actually pretty easy because all we have to do is just rewrite them. That's it. Evaluate the limit. We want to find this limit by interpreting it as the limit of Riemann sum of a function on the interval from a to b. Now remember, if we want to do this using the method of earlier section, we can still do this one because it involves k. It's algebraic, but this one we don't have. We cannot write that as a function of n that easily. Okay, so let's actually define what this means. The first limit of the sum, right, in number 60, that one is just going to be, let me call the limit L is going to be, I can write that as the integral from 0 to 1, right, of the function is just going to be k to 1/3, right? So that's going to be x to 1/3 and then dx. Now, where did the n go here? Remember, with the limit of Riemann sum, we assume that this is like n, the denominator becomes, let me write it over here. Denominator becomes 1 over n to 1/3, which is 1 over n. And remember, we're going to call that our delta x. So this is in the form f c sub k times delta x. Okay. And that is exchanged with a dx in our definite integral. So for number 60, that's the definite integral. And now we can actually do that limit, right? Integral of x to 1/3 is x to 4/3 divided by 4/3 makes 3/4 in front. So interpreting as a definite integral, look at how fast we do these limits. There you go. And that's going to be 1 to 4/3 minus a 0. So the answer is going to be 3/4. Boom, we're done. See how fast that was? In number 62, the limit of the Riemann sum, right? And for this one, again, let's see, we can write number 62 as the limit is. What's important is the function in front, okay? The constant doesn't matter in front here, right? So that's going to be the integral from 0 to pi over 2 of cosine x dx. Okay, and here, if you think about u is k pi over 2n, then du would be what, pi over 2n dx, right? And there you go, that's the front part that makes it work. That's that part. Okay, so that's what the definite integral turns out to be, and this will be the integral of cosine s sine from 0 to pi over 2. Sine of pi over 2 is 1, sine of 0 is 0, the answer is 1. I see. Okay, and that's it. So we're good with this one. Let's see, and the same thing what I did here up front here, that works for this. If you let u be like k over n, then your du is 1 over n and then dx, right? Or actually, in terms of integral, k becomes x, right? Okay, and this one too, k becomes x. When we move to definite integrals, the k's turn into x's. Okay, and we're good with this work. All right, and with that, we are done. We are done with this section on Fundamental Theorem of Calculus.